My name is Nadia Smith. I am BEKA Schréder's Senior Communications Officer. Welcome to our webinar. Thank you for joining us. We look forward to presenting to you the Introduction to Street Lighting Basics this morning. If you have any questions during the webinar, please type them into the question mark tab and we will answer them after the presentation. Please note that there are some brochures available for download in the Handouts tab. Joining us again this morning is France. She is the Training Project Manager at Schréder, and she will assist us with this platform in the background. Some of us are presenting from home, so as always, please excuse any unusual noises in the background. Derek Watson, our Commercial Manager, will give a brief introduction about the company, and Retief Kutzer, our Lead Design Coordinator, will present the Introduction to Street Lighting Basics to you. As mentioned before, this will be followed by a Q&A session. And then finally, we will ask you to complete a short poll to give us feedback. I'm now handing over to Derek.
Thank you, Nadia, and good morning, everyone. I'll give a brief company introduction again because I've noticed once again many additional new attendees to this webinar since our previous ones. So the company, which was founded in Namibia in 1978, moved to South Africa 39 years ago in 1981. We are Africa's leading manufacturer of luminaires and GRP, or glass fiber reinforced polyester poles, as a level 3 certified company, and we currently employ about 320 people. We've been a member of the global company Schréder since 2002, becoming wholly owned by Schréder in 2013. This allows us to embrace the latest technologies such as optimizing light control technologies, for which Schréder is certainly well renowned. On the next slide, we see an overview of our head office and manufacturing facility. Sorry, I have a little lag. As a company, we consistently review our manufacturing, logistics, and operational capacities, and this ensures we are able to continuously provide our renowned high levels of supply and quality efficiencies for our many customers. So moving on, the company, BEKA Schréder, we're the first South African company to be the lighting company to be awarded ISO 9000, being the Quality Management System accreditation way back in 1989. We have this year initiated audits for accreditation of both the ISO 14001, being the environmental management standard, and the ISO 50001, the energy management systems. These should both be completed sometime this year. Our commitment to save energy is not only through our processes, but very significantly through the design and implementation of highly efficient products, which are designed and manufactured within South Africa. Our success can certainly be attributed to the ongoing research and development of new luminaires and pole solutions, which meets the ever-changing demands of our lighting landscape. We, as a proudly local South African company, are committed to utilizing downstream manufacturing of components in South Africa. We use our products wherever practically possible, utilizing downstream manufacturing, designed and performed to perform well within our harsh local environmental conditions. Just taking a look at our lighting solutions as a design and manufacturing company, we offer lighting solutions for virtually all projects and product segments within our markets, be it the ambient segments, road and street lighting, various flood lighting applications, industries and mining, commercial and illumination marketing segments. Whereas the emphasis of today's webinar is naturally based on the road lighting segment. And finally, our company has a team of accredited lighting practitioners with many years of collective design experience, available to meet all your design needs, being fully proficient and flexible in providing solutions for virtually all aspects of lighting applications. Further to this, results such as ROI calculations, return of investment, 3D modeling, etc., are all easily submitted by our team of specialists. And now let me hand you over to Retief Kutsa, who heads up our applications department. Retief will present today's topic being street lighting basics. Thank you, Retief.
Thank you so much, Derek. Good morning, ladies and gentlemen. It's a pleasure for me to be able to provide you with this knowledge. It's always nice to interact, albeit in a digital manner. I hope this will be an informative session. There's a lot to go through because this is the foundation of street lighting. So there's a bit of information to understand and get to grips before we can start really understanding road lighting and street lighting. So I'll just go through the contents. What we'll be discussing today is broadly the basics of road lighting design. More specifically, we will be focusing on the essential terminologies and metrics that's needed to understand a road or street lighting design. I'll give a brief history on electric road lighting, as I think it's always interesting to know the origins of these things. And I'll explain the coordinate system in reference to streetlight luminaires, and then delve a little bit deeper into photometric data, which will include the polar diagram and Schréder's really cool hypergon. Finally, I'll briefly go through the relevant South African national standards requirements for Class A roads and B and C streets. And then I'll explain how to interpret a road lighting report. In this case, that's been generated by the Ulysses 3 software. Okay. In 1870, Pavel Yablokov, as you can see, here's a picture of him on the right, was a Russian electrical engineer who invented the Yablokov candle in 1876. There you'll see what it looks like there. It mainly consisted of two carbon rods separated by plaster of Paris, and with a small piece of fuse wire or carbon paste linking the two rods at the top. Once electricity was supplied, an arc was struck, and by consuming the electrodes and the plaster of Paris, it created bright visible light, much like a candle consumes the wax and wick to do the same thing from the top down, only much brighter. It was first used for street lighting in 1878 on the Avenue de l'Opéra in Paris, France, using 64 lamps with around 4 to 12 candles each. The disadvantages of this lamp were numerous. They needed constant replacing due to the burning of the carbon rods, produced an audible buzzing noise, and carbon monoxide, as well as radio frequency interference. The potential for dangerous ultraviolet light was also high should an enameled glass globe break. However, the advantages were weighed against the performance and cost measured against the old gas and oil type lighting. This lamp type produced very bright illumination, and at its peak, it cost only 10 cents in francs at that time per candle. The first streetlight luminaires in South Africa were installed in Kimberley on the 2nd of September 1882 on the Toitspan Road. There were 16 luminaires installed, of which 4 were placed on the corners of Market Square outside City Hall, pardon me. This means South Africa was an early adopter of new technology a mere 6 years after the invention of the Yablokov candle. And if you look at that image, you'll see the replica of one of those initially installed luminaires on that street there. And then a very old image of the Toitspan Road with the original lamp there. These were swan lamps that were used in 1882. Okay, we're going to quickly go through the definitions that are very important to be understood when looking at road lighting design. So I'll move through these. We have a lot of substance to go through, so I'll try to do it as quick as possible, but without neglecting the definitions or the metrics. So the first metric we're going to discuss is luminous intensity. The luminous intensity is the power of a light source to emit light in a given direction. It is the luminous flux emitted per unit of solid angle or steradian. The luminous intensity is a quantity for characterizing a light source and its perceived brightness. It is defined as the luminous flux per unit solid angle. The standard international units of luminous intensity are candela or lumen per steradian. 1 candela approximately corresponds to the luminous intensity or the perceived brightness of a normal candle. Luminous flux is the flow of light in space. It is the total quantity of light emitted by a light source per second. The standard international unit of luminous flux is the lumen, and 1 lumen is defined as the luminous flux of light produced by a light source that emits 1 candela of luminous intensity over a solid angle of 1 steradian. Luminance is the luminous intensity divided by the apparent or projected area of the source or surface. Simply put, luminance describes the amount of light that is emitted from, passed through, or reflected off of an object. It is measured using candela per square meter, which is the concentration of luminous intensity per unit area in a specific path. And a simple way to remember the difference between luminance and illuminance is that you can see luminance. You cannot see illuminance. Luminance, you'll see the image to the right there, is defined again as the brightness of light that is reflected or transmitted off or through the surface in a specific direction. It is measured in candela per square meter. Luminance is also considered the human perception of brightness, or how bright we perceive surface n, the amount of light falling on the surface. Then illuminance is the amount of light striking a surface, also known as the incident light, where the incident is the beam of light actually landing on the surface. This you'll see later on becomes is relevant to your B and C types or classes of road as per SANS 10098 part 1, and the luminance is part or is relevant to the A classes of road for in SANS 10098 part 1. Okay, then we'll move on. Road surface reflection is a function of the physical state of the road, its nature, the direction of illumination, and the conditions of observation. Here you'll see a table showing all the different reflection factors used internationally, and there are many more. This can change. It's almost innumerable, but these are your standard reflection coefficients. Different pavements have different reflection characteristics, which depend on the texture of the surface, its age, the materials included in the pavement, the binding materials, the paving method. And you'll see that we in South Africa base our standard calculation on a reflection factor of R3007. This is a slightly specular reflectance, typical of asphalt surfaces with dark aggregates, rough texture, and some months of use. Some months of use means basically we're using a reflection factor that is typical of a new tarred road. This surface is common in the United States, but it's also the one we use as per CIE 140 in South Africa, and that is what our standards are also based on, is CIE 140. It's also a conservative way of calculating the spacing between poles, because if you went up to an R3008 reflection coefficient, you would have a slightly more specular type of reflection, a bit more mirror-like because of all the driving and friction over time on that road, and this would inevitably potentially give you the option to increase spacing, but it's not what's done as a standard practice, and this is something that you, the client, will be able to tell us, listen, this is a R3008 road, please design according to that. But generally we will stay to a R3007 new asphalt reflection factor. Okay. In street lighting, it's also important, obviously, to know and be able to understand the orientation of the luminaire. In order to do this, it's necessary to know the standard coordinate system used to photometer a streetlight luminaire. There are two axes that are used, known as the horizontal or azimuth angle and the vertical or gamma angle. And in this little animation, you'll see that you'll see these planes. You'll see C0 is to the right of the luminaire as it's facing the road. C90 is to the front, roadside, also commonly known as roadside. C180 is to the left of the luminaire as it's facing the 90-degree angle, and C70 degrees is as it's behind the luminaire, or commonly known as the house side. So for the horizontal axis, the luminaire is photometered according to the CIE system of allocating horizontal angles relative to the position of the lamp, where 0 degree indicates the right side of the lamp, 90 degree the street side or front, 180 degrees is the left, and 270 degrees is rear or house side, with 360 degrees being the same as 0 degrees. The horizontal axis is divided into 52 measuring angles, and are also known as the azimuth angle, or more commonly the C angle. The vertical angles, which you'll see there in the animation, for the vertical axis, also known as the gamma axis, the luminaire is photometered according to the CIE system of allocating vertical angles relative to the lamp. 0 degree indicates the position directly underneath the lamp, also commonly known as the downward vertical or nadir, with 180 degrees being the position directly above the lamp, also known as the zenith. The vertical axis is divided into 36 measuring angles, also known as the elevation angle, or more commonly the gamma angle. And when measuring the luminaire is secured with the lamp in horizontal position, if there is a lamp, and is scanned for the intensity value expressed in candela per kilo lumen, which I'll come to just in a slide after this, at 0 degrees vertical. Through all horizontal angles, there are two half planes. The first half runs from 270 degrees, which is behind the luminaire or house side, through to 0 to 90 degrees, which is street side. And then the second half is run from 90 degrees through, which is street side, through 180 degrees left of the luminaire back to 270 degrees, which is behind the luminaire or house side. This same process follows for the next and each following designated vertical angle. The total number of measurement readings is 1,872. The results are then published in an intensity distribution table, commonly referred to as an I table, indicating the intensity in candela per kilolumen at each horizontal and vertical angle. This table can then be converted to a data file for use in various street lighting design applications or programs. Now I'll just move on to the polar diagram. The polar diagram is something you'll typically see in any manufacturer of luminaires' catalog or brochures, and something that is quite often happens is clients or stakeholders don't really. A lot of people are afraid to ask questions about the polar diagram. And it's actually a very simple diagram to understand, and that's the intent of this slide, is to just make this a little bit more clear. When looking at the polar diagram, you will notice three distinct planes, of which two were mentioned in the previous slide, and their corresponding intensity values in candela per kilolumen at different angles. The candela values are expressed in candela per kilolumen for a good reason. Instead of making 2 or 20 different polar diagrams for the same photometry or lens that was used at different correlated color temperatures or driving currents, we simply plot the results for 1,000 lumen or 1 kilolumen. This means, very simply, that if a lamp has a nominal output flux of 2,000 lumen, we would simply multiply by a factor of 2. And if it has a nominal output flux of 5,000 lumen, we would multiply by a factor of 5. It's really that simple. You'll see in that image there, I've tried to make it very clear what you would, how the flux is emitted, how the luminous flux is emitted from the luminaire. In red, you will see I've created the luminaire, the physical shape of the luminaire. In the top right-hand window, I've called it top to bottom, or if you like, zenith to nadir, or even 180 to 0, because those are, we're looking down the vertical. Then to the left, you will see the 90 to 270 plane. As you can see, the luminaire is facing 90, with 270 being house side. So it's facing street side with the tail going to house side. And then looking at it transversely, you can see the 90 to 270 plane. And then if you look at the bottom right-hand screen image, you'll see the luminaire as viewed from either standing behind the luminaire facing the road, or it would look exactly the same if you were standing in front of the luminaire facing the house side. So 0, 180 degrees is a fixed plane, as you can see here. You would see the flux emitted from the luminaire when either standing behind it at 270 or facing the road, or from 90 facing the house side. And I've just highlighted it here in yellow so that when you look at that polar diagram, you can see this fixed plane of 0 to 180. And you'll always get two fixed planes, a 0 to 180 and a 90 to 270. And then to the right, to the bottom right of the 5305 optic, or from that polar diagram, you'll see another plane called 15 degrees to 165 degrees. And that's a variable plane, but it must always be shown. This is your intensity maximum plane, and I'm going to get to that. The 90 to 270 plane is also a fixed plane, as I've mentioned, and it's how you would see the flux emitted from the luminaire when you're either standing at 0 degrees, which is the luminaire right, if you like, right, facing the luminaire at the right angle. Simply put, it is what you would see when standing in the street, facing down the street towards the luminaire. And I don't know if any of you drive on very early mornings, especially now, these days here in Johannesburg, when I drive on the N1 and then the R21, early in the morning, there's lots of mist and fog, and you can actually rather clearly see at least the 90 to 270 distribution. Then as we go to the IMAX plane, which I've explained at the bottom right, it sits at the bottom right of that polar diagram. I'm going to try and explain it to you a little bit more clearly using Schréder's hypergon imagery to explain how that flux is emitting from this luminaire, from this specific optic as well, 5305. So if you look at that image, you will see all the azimuth angles from the right, going from 0 degrees all the way in an anti-clockwise direction back to 360 or 0, which is again back to on the right-hand side of the luminaire. At this, you can now see that the 90 degree is facing the street, with 270 degrees being behind the luminaire. Now, where is the IMAX? Where is that intensity maximum plane? I've overlaid this image here, and you can see quite clearly that at 15 degrees to the right of the luminaire, at about 65 degrees vertical, there we have a measured intensity of 636 candela per kilo lumen. And then as you go anti-clockwise back to the 165 degree plane, you'll see that exact same angle, a 15 degree angle, but in the 90 to 270 plane. So that is a very simple explanation of the intensity maximum plane. You'll always get these three planes. You should, and it will explain how this flux is being emitted from the flash area or the luminous opening towards the street, what the light distribution going back towards the house side might look like, and then you can in your mind start understanding how this luminaire with this optic might interact with the environment where it's being considered. So we can now clearly see where the IMAX measurements are, also known as the peak intensities. And in this case, with this optic or lens, they are at 15 and 165. The variable plane of this variable plane is the flux emitted where the intensities measured are at peak. Okay, and I think this is a wonderful way to understand the optical control of the flux emitted by the luminaire. And obviously you can start inferring that if the intensities were pushed forward a little bit more, let's say rather than 15 degrees, they were at 20 degrees in the IMAX plane. So 20 that shows you that the light is being pushed forward. So potentially you could cover a wider roadway, but that might have an effect on spacing. It's good to understand how the flux being emitted from this luminaire could potentially be used on different types of road geometry. Okay, so I think we've covered all the necessary metrics and understanding a polar diagram. And now I'll quickly go into the standards, the SANS 10098 Part 1 standards. Okay, we've covered the basic metrics and understand a little bit better the photometry of a luminaire using the polar diagram. We can quite easily interpret what is expected when applying standards to road and streets. A-class roads are roads where luminance is necessary to be measured. In other words, the light can be seen after having interacted with a surface. As I've mentioned earlier, luminance is something that we can see. It's perceived brightness, and we see it in candela per square meter. In A-class roads, there are 4 different categories of road based on the speed traveled. These are then subdivided into 2 main subdivisions where a median is present or not present. Each of these 2 subdivisions is then further broken down to the known volume of traffic in hours of darkness, of which there are 3 distinct volumes for each class of road, with or without a median. The category for the category with the highest luminance levels and the lowest TI is typically your A1 no median 600, which is based on the inherent risk associated with the speed of travel and the volume of those using that road. You can understand that traveling at 120 kilometers legally in South Africa with 6 lanes on the road it has an inherent risk, especially if the road is frequented by many road users. Obviously, in this case, legal road users so cars and motorcycles that are allowed to be on that class of road. And for this type of road, we have to have a very good luminance. We have to have a very good overall and longitudinal uniformities and a low TI or a low threshold increment. And I'll get to those terms now. The category with the lowest luminance levels and highest allowed threshold increment is the A4 median 200, which is based on very low volumes of road user in hours of darkness and at relatively low traveling speeds. And you can see that there's a very good description in the left hand where that green rectangle is of each type of class of road. So A1, where it says freeway and expressway with a median or without a median, obviously free of level crossings for speed limits exceeding 90 kilometers an hour. And then all the way down to A4, these would be your connecting roads, local distribution roads, residential major roads, before we start going into illuminance type roads or streets rather, with a nice description at the bottom of that table of all the relevant definitions that need to be understood. Now, the first definition in that for each type of road, with whether it's with a median or without the median, and once we know the volume of traffic in hours of darkness, the first one is luminance, the minimum average luminance, and this is the portion of the road known as the calculation area, is the area represented in the longitudinal distance between the 2 lighting masts or poles on the same side of the road, and in the transverse distance between the white line on the right and the yellow line on the left. The observer is 60 meters away from the front of the boundary of the calculation area, at 1/4 the carriageway width from the left-hand side, at 1.5 meters above the ground level, obviously facing down the direction of travel. The overall uniformity, this is the minimum value of luminance at the calculation point within the calculation area, divided by the average luminance within the calculation area. So this is your minimum to average, and this is purely for performance. This is making sure that we can, as road users, safely see from 60 to 160 meters away any object that might be in the road and gives us time to take safe evasive action. That's for performance. But then we have something called longitudinal uniformity, which is very important for visual comfort. This is calculated along the center line of each lane. The observer is also 60 meters away from the front of the boundary of the calculation area, but is situated on the center line of each lane. It is the ratio of the minimum luminance along this line to the maximum on that same line. So here we're measuring the minimum to maximum, not the minimum to average. and that actually gets rid of an effect called the zebra effect, if you like. Overall uniformity is minimum to average, but the longitudinal is minimum to maximum, and that has the observer testing it in each lane. Threshold increment is the final metric or prerequisite that needs to be achieved within the limits that are allowed. And this is the percentage increase in contrast required between an object and its background for the object to be seen equally well with a source of disability glare present. And I know I've presented on this before, but you have two main types of glare. There are others. There's one more, but in this case, we're going to talk just quickly about disability glare and discomfort glare. Now, TI is a measurement of disability glare. It doesn't cause any, how can I call it, physical discomfort, but it is a very dangerous, obviously, in this type of environment, because a typical example, as we all know, is driving at night or early in the morning, even especially on a wet road, when you have someone with their brights switched on coming in the opposite direction. You don't necessarily feel pain as you over time. You don't necessarily feel pain, but you become blind. You cannot see. It's called veiling luminance. The light causes a type of veil, if you like, extraneous light inside the eye, and it obscures what it needs to be seen. Okay, then moving on to B-class streets. Just for your information, a street and a road. A street is something is normally determined by the fact that it has walkways, walking areas next to the road. So it's generally in built-up areas where there are residences and shops and so on. That's just for interest. B and C class streets are where illuminance levels are considered. So that's the type of light that can be measured but not seen. It is we designed for illuminance in these areas because they are more dynamic areas regarding the type of road user. So you have, I mean, on an A class type road where we're working with luminance, you're really only expecting that you're going to be sat in your truck or motor vehicle or motorcycle, looking ahead of you for extended periods of time. But in a B class road and C class, you're looking at it's a much more dynamic environment. You have cyclists and runners and motor vehicles and the neighbor's cats, and these all could potentially pose risks to the person using the road. So therefore, we intend to ensure that there is enough volume, if you like, of light in space in this area, so that on the road, the measured incident light will not be lower than the required standard. The environment is such that the driver might not be, as is the case with A-class roads, only looking ahead for extended periods of time, but rather that they might be expected to look around more often in order to avoid that neighbor cat or the kid or another car making a bad decision. So there are three subdivisions of B-class street, the highest being B1 and the lowest being B3, with a minimum of 0.4 lux. So you'll see B1 is a residential street, or typically classed as a residential street with medium to high volume of traffic, equaling 5 lux minimum maintained average, with 1 lux minimum. That is normally the limiting factor, is the 1 lux minimum. And then you go down to B2, residential streets with medium volume of traffic, and then B3, residential streets with low volume of traffic, where we have a 2 lux minimum maintained average, but with a 0.4 lux minimum, which is the limiting factor. So as a matter of interest, a full moon at perigee, when it is closest orbit around the Earth, over the tropics, will produce around 0.3 lux minimum. So if you've ever walked at night by moonlight here, you will have a good idea of what you can visually expect from 0.4 lux minimum. Generally, when the moon is not at perigee but at apogee, which is the furthest away in orbit from Earth, you can expect anything from 0.05 to 1 lux, 2.1 lux minimum in the ambient environment. And that's a nice way to understand these minimums. Also in B-class streets, you will have, also in the illumination class of streets, you have C1 and C2, which are wholly pedestrian. In the city center, for instance, you have a very high minimum average, minimum maintained average lux level of 10 lux with a 3 lux minimum, and then C2, which is wholly pedestrian and in local shopping malls. And I know in Europe, for instance, you have areas called high streets, which are actually completely blocked off to motor traffic. And they also refer to those type of areas as a mall, although it's not under a roof. And here again, it's a 7.5 lux minimum maintained average with a 1.5 lux minimum. You'll also note on the right-hand side of that table that there is something called minimum semi-cylindrical illuminance. And if you look at the bottom at note B, it says it is for areas requiring higher security. Semi-cylindrical illuminance values, as stated, can be used as a supplementary criterion. They apply on the footways parallel to the curbs in both directions. So simply put, what happens here with minimum semi-cylindrical illuminance is we would calculate the illuminance on a semi-cylindrical half cylinder, if you like, at 1.5 meters above the ground in both directions along the parallel to the road on the sidewalk. This has a very good effect on understanding. The reason you would do this is to see the intent of the person walking towards you, or you're walking towards, and it's generally used in high crime areas. So, but it has a very, very harsh impact on spacing of poles. But it's good to know what it's for and that there is a provision made for such areas. Okay, we'll then move on to the software that we use. And in this case, we're using Ulysses 3.5.2, which is the latest version of Ulysses. You'll see the database version there is 2020. That's this year, January the 29th. So it's the latest version of Ulysses. And what you can expect to see in such a report, the most important bits of this report. Now that we have a foundational knowledge of the metrics of a polar diagram and of the differences between the classes of road or street, we can now interpret the design or the report that is produced by the designer. We can interpret it much better. So now, typically what we would do for Ulysses 3.5.2 is, once we've done the calculation, we would go and generate a report of which there's obviously the front page explaining exactly what is going to be seen. So in designing for a road or street, it is important to ensure that you show the client the luminaire or luminaires that will be used for the results. So you will put a nice image of the luminaire to be used or that was used for the calculation. You must then show that standard which was used to calculate the results. So our standards are SANS 10098 part 1 and 2, and they're based on the CIE 140 standard. So you can see that that is the standard that was used, if you look just below the luminaire, to do the calculations. It's also important to be able to trace a design to the designer. So we include the designer on the front page. And then finally, we give a very good overview of what the client can expect to see throughout their perusal of the report. So typically, you would want to, once you look at this design at the front page, you should clearly understand exactly what you will be seeing when going through the rest of this, if you like, storybook, this report. When we create this is a pseudo intensity diagram or a false color image, and these types of images are not part of the default contents of Ulysses, but it's very important for us to communicate as a designer clearly, as clearly as possible, what and how a design was done. So that is why images such as the pseudo intensity diagrams, we choose to include them and are shown in an isometric fashion because it gives you a three-dimensional environment where you can see the poles and luminaires and how they're situated in space in reference to the road, as well as the overall geometry of the roadway. So this is once you see this, you can see, oh, hold on, it's accurate, or no, there's something missing. Where's the cycle lane, for instance? And this is a nice way to quickly see, just as a broad overview, has the designer calculated correctly? You'll also obviously, like I said, you can see there's the setback of the luminaire, but we're going to get to another slide where that is made clear. I'll quickly go through the next 5 slides just to ensure a simple understanding of these images that can be generated by the designer in Ulysses with the client's ease of understanding in mind and as the main prerogative. So like I said, this is a pseudo intensity diagram. This is a very nice way to understand, because a lot of the time it's one thing to see 2 candela per square meter with 40% overall uniformity and 70% longitudinal uniformity. But what does that mean visually? What am I expecting as the road user? So when you look at the pseudo diagram, you can see in false colors, that, you know, and I'll show it in a little bit of a later slide. There's a scale, but you can infer where there's now a light blue or a green area on the road. And please always know that when calculating for A-class roads, the surface that is frequented by the vehicles in general, so that's the driving surface, that is where we calculate. We can calculate on hard shoulders and so on, but that's not required by the standard. So if we only look at the driving lanes, you'll see that there's a green area right between the luminaires in the center of the first lane. That would potentially be the brightest spot of lighting, and then it starts shading into a pink where you might have a darker area, but it's dark relative to the bright. It's not, there's no light, and we'll see that with the legend a little bit on. You'll also then see a calculation grid, which we also include, because it's nice to have all the images showing all the different visual interpretations of what you can expect. And here you will see all the candela per square meter values measured at those individual points, and your ISO lines connecting all the line basically connects all values of the same candela per square meter value, and then you have this really nice interpretation. So you'll see I've in a later slide where I've superimposed these, and it gives you a very good understanding of how the light is interacting with that area and how the observers are experiencing this driving environment. Finally, we also include a cross-sectional view. Generally, we say left, but it could be right. It doesn't matter. Just to show the rake, whether this luminaire has been raked or not, and where the peak intensity of this optic is sat. So you can see this luminaire was not raked, which is always a good thing, specifically with regards to glare or threshold increment. And you can see that the peak intensity on this luminaire is quite far. It's actually reaching almost to the opposite side of that second lane, or the fast lane, if you like, if this was going in one direction. Then we create this image that we build to show all the geometry in meters. So you can see that here we used a 9-meter pole. It was 1 meter set back from the yellow line. You can see it's got a 150 mil spigot, so no real outreach, and we're achieving a 46-meter spacing to the relevant standard, and I'm going to get to that point. I've included 2 hard shoulders, and there you go. That's a 9-meter pole covering about what, 12-meter, 13-meter, or 14-meter road cross section. We'll move on. You'll also then see all the information necessary about the luminaire that was used, as well as the optic that was used. In this case, it's a 5307 optic. And to the bottom right, you'll see the polar diagram, which I've showed you earlier. You can see the 270, 0 to 180 and the 90 to 270 plane. And now you understand them because they're fixed, but you also have your Imax, your intensity maximum plane, or your peak intensity plane, if you like. And you can now interpret how that will interact with the space. And obviously this is a basic. You have to see the luminaire that was used. Now here is where you will see what was calculated and how. we can see that going from the top to the bottom, there's a left hard shoulder. So that's obviously on to the left, where you can see left hard shoulder with the vehicle facing away from us. And then there's a right hard shoulder with the vehicle facing towards us. So coming down, the important bit is the area that's used by the vehicles for general travel. So we'll see that we have calculated to an A3, no median, 300 class road as per SANS 10098 part 1. And to the right of that in bold, you will see it gives you the parameters that it needs to be compliant with. So we need to achieve 0.6 candela per square meter, an overall uniformity, which was your minimum to average of 40%, a longitudinal uniformity of 50%. And by the way, longitudinal uniformity will always be higher than overall uniformity. And then finally, your threshold increment, which is your percentage increase for disability glare for sources of direct glare. And there you can see we're achieving in lane 1 for observer 1, we're achieving 0.64 candela per square meter. We're 43% overall uniformity. We're looking at the 53% longitudinal uniformity. And then at the bottom, the TI is perceived as 15.3. So we're far under the 20% allowed. And then observer 2, you can see is a 0.71 candela per square meter luminance. So we're achieving quite comfortably the 0.6 required. We've got a 41% minimum to average, so that would have possibly been the limiting factor. And then you have a longitudinal uniformity of 61%. This is where I would explain the first 3 images, the pseudo intensity diagram, the calculation grid, and the ISO lines. And here you can see this is typically for observer. It says absolute 1, that's observer 1. Standing 60 meters away in facing the direction of travel, and you can see that they are perceiving from that position at 1.5 meters above the ground with a reflection factor on the ground of R3007, a 1.3 candela per square meter maximum with a 0.28 candela per square meter minimum. We then overlay the ISO lines, and we can see how that we're starting to build a visual interpretation in our mind of how this intensity of how the light that we actually see might look, and where we can expect bright with reference to dark, or dark with regards to bright, and then the pseudo intensity diagram. And that's a very simple way of understanding those 3 images that we include. So you have an isometric view, and then you have this plan view facing down. Also, you can see the way the flux is emitted by those 2 luminaires on the pole or on the poles. And then you have the exact same for observer 2, absolute 2. Okay, so that's in a nutshell the basics you need to understand so that you can interpret road lighting design. And these are some of the things we have to take into consideration at all times. I'm going to quickly summarize what we've been through. The first thing was the Jablokov candle, and that South Africa was an early adopter of street lighting. In fact, we had the first street lighting, electric street lighting in the Southern Hemisphere. So take that, Australia. We then moved on to the various understanding these metrics, and that you have your light output, which is luminous flux. That's the flow of light in space. You had your light level, which illuminance, lux, or in America, it's foot candle, lumen per square foot. The lux can also be called lumen per meter square. And this you cannot see, but you can measure. It's the light incident on a surface. Then you had your luminous intensity. This is the candela. We saw earlier that you can measure 1 candela per steradian in a meter square, a sphere, or a sphere with an area of a square 1 meter. And then you had your brightness, your luminance. This is what you're actually perceiving. This is what you're seeing, and that is measured in candela per square meter, or in the States, candela per square foot. This is my attempt with my ninja skills at paintbrush in explaining how a luminaire is facing the road. So you have your road side 90 degree and your house side 270 degree. right of the luminaire is 0 degrees, left of the luminaire is 180 degrees. The blue being the emitted flux, which is lux, you cannot see but measure, and actually you measure it at the surface. And then the yellow being how that light might fall onto the surface, having reacted or interacted with the R3007 reflection factor or other reflection factors, and how it might look. This is the hypergon, just to show that at 180 you can now see where that, this is the exact same optic that I showed you earlier, the 5305. You can see it's at about 65 degree peak intensity to the left of that luminaire, going to 180 with a 15 degree towards the road, as well as at the bottom right with your legend in candela per kilo lumen. We explained that A-class roads are luminance type roads where reflection plays a big factor, and that this is for the light that you can actually perceive visually. And then that you have your B and C-class streets where illuminance is measured and calculated for, and this is the type of light you cannot see but can measure. Any questions?
Hi. Okay. Yes, we actually have quite a few questions. But now also, if you have, please, if you have any questions, please type them into the question mark tab. I will start off with the first question here. What is the difference between .ies and .ldt photometric files?
Hi, can you hear me? Hello?
Hello, Retief.
Hi, can you hear me?
Yes, I can hear you. Did you hear me?
Yes, yes. IES is the international, is the Illuminating Engineering Society of, it's an American file. It's part of the IES. ULUM-DAT files is European, and it typically tends to have much more information in the background. That's a very simple explanation of IES and LDT. Also, the orientation of the luminaire is different. It's for IES files, typically they would see where we see the street at 90, they would see 0 as the street side and 180 as the house side, where ULUM-DAT is, as I've just explained it to you, the 90 is at street and 270 is at roadside, at house side.
Okay, thank you. Then here's the next one. Do BEKA's polar diagrams on brochures show optic or luminaire system luminous flux?
It shows a luminaire system flux, as far as I understand. It not the nominal flux, the system flux. So you'll see nominal flux, which is at chip level, but we take into account the losses and maintenance factor, and we create, and the polar diagrams are created to show system flux.
Thank you. Then here's
Sorry,
the next one.
Nadia,
Yes,
may I just
Derek?
add to that? So what we have started doing in many of our brochures is we're showing both, because there is occasionally confusion and misunderstanding between system flux and output flux. So in many of our brochures going forward, you will actually notice on our tables, we reveal both of them, that you are aware of the difference between the input flux versus the system flux and the output flux.
Okay, thanks, Derek. Then the next question is 5305 optic good for UL and narrow roads, as UO is impacted for wide highway type roads?
Look, to answer that question is it's a bit ambiguous in how for me to answer that. It's 5305 is a good optic for the right application is the best way I can answer that. It is it's a very, as you've seen, it's got a 15-degree peak intensity to either side of the 0-180 plane. It has a 65-degree peak intensity if you look at the verticals, and for narrow roads it should be a very good luminaire, but it might also be good for a different application where you might have a third or a fourth lane. It depends. I don't know how else to answer that question. It is the optic. We will always test all the optics to get the best performance, lowest wattage, biggest spacing, lowest pole for the relevant application.
Okay, thanks. Then we've got, well, Retief, if you could please confirm the definition of the carriageway, and is it part of the standard SANS 10098?
Yes, as far as I'm aware, it is the area between. It is the area that is used not just not just for the entire roadway. It is the area for the which the vehicles use for general travel. It is not for the hard shoulders. But I will go and find it, and I will send the answer to the questionnaire.
Okay, that's fine. Then moving on, which criteria would be most important regardless of speed limit and traffic volume, and why? Is it candela per square meter, UL, UO, or TI?
Okay, hold on. So there's a lot to attend to in that question. What was the just repeat the question, please?
Sure. Which criteria would be most important regardless of speed limit and traffic volume, and why?
Okay, so if we're talking about A-class roads and we have to take speed out of the equation, then I would definitely say overall uniformity and longitudinal uniformity would be your two most, and then your TI, and then your candela per square meter. So I hope that answers that question. However, taking speed out of the equation wouldn't be smart, because that is what is causing the risk, is the speed. So the speed you're traveling at actually would have a major impact on which criteria can be considered most important. You will see that the standards put quite a high emphasis on longitudinal uniformity. So if you just looked at that, you would see that longitudinal uniformity is very important, threshold increment is very important, the overall uniformity is very important, and then the candela per square meter, which is what we're perceiving visually, as well as the uniformities, is also very important. But if I had to put it in order of importance, it would probably go UL, UO, TI, and then candela per square meter.
Thanks, Retief. Then the next question, where can I download Ulysses 3.5.2?
I think that's a question for marketing, but I'm sure it can be made available for or to clients.
Hi,
Ron, did you want to confirm that?
Yes, yes, sorry. Hi, my name is Grant Comrick. I'm the Marketing and Separate Development Manager. Yes, we'll definitely be able to make that available to you.
Okay, thanks. Then the next one. What legal implications or responsibilities are there for a lighting designer? Can a client hold a designer responsible for poor lighting designs?
Well, first of all, I think yes. A lighting designer can be held responsible for bad lighting designs, definitely. But it's something that I think there's also a bit of an ambiguity there, because when we design, we take into account, we do a very thorough due diligence with regards to the environment that we're designing for, the reflection factors. if, for instance, let's give a theoretical example. A client tells us, please design for a B1 class road with 2 lanes, 2-meter setback, 7-meter pole, 8-meter pole, and the best luminaire. No problem. Then we do that. The design would be very good, potentially, in a theoretical fashion. But once installed, the client finds that there are trees in the way, the geometry is actually a little bit off, it's not exactly as per the request. Then you see what I mean? Who's responsible there? What the designer can only design and ensure that they can show they've taken every necessary precaution to make sure that the design is as accurate as possible. Legal implications, I'm not too sure. As far as I am concerned, if someone has been, look, I don't even want to venture a guess there. Legal implications, I would rather just say I don't know what the legal implications are than say I know what they are. I'm sure there could be legal implications, not in a criminal fashion, I'm sure, unless it can show that there was gross neglect and the designer really did such a bad job that it should. But again, then you have to take into account the person signing off on it has to go as to also be take that responsibility. So it's a hard question to ask or to answer accurately. I hope I have answered it in a way that makes sense. We as designers have a very big responsibility to ensure that we take all the information that we have. If there's anything missing, we ask for it. Once we have it, then we do our utmost to ensure that we have applied due diligence to the design, and then we can send it.
Okay, thank you. Then the next one, in addition to compliance to SANS 10098, what about design consideration relating to light pollution, environmental conditions, universal access, NMT, etc.?
Yeah, look, we also take into account the Dark Sky International Dark Sky Association. It has to be asked for. Look, it's not a consideration in SANS 10098. But when you go to 10398 Part 2 and you start looking at specific environmental zones, now there's an additional zone of 0. So you've got zone 0 to zone 4. It's something that can be requested, and then we have to do a major study and get some other experts involved to tell us what kind of, for instance, if it's a zone 0 or 1 or 2 or 3 or 4 E-zone, environmental zone, we need to have some kind of study done to see what kind of wildlife is there that might be impacted. But then if we're talking about dark skies, we make sure that there is no upward lighting element in any of our road lighting luminaires, and if there was, it's something that has to be taken into account and the client needs to be made aware of it. So that's one of the wonderful things of LED, is that it's so controllable. That light pollution, when it comes to street lighting, especially with LED, is non-existent when measuring it from the luminaire. Obviously, you cannot limit the light reflected off the surface, which can cause light pollution. I hope that's answered. I hope that's answered the question.
Thanks, Retief. We do, just going back to the previous question about being held legally liable. Someone was kind enough to assist us here, and he said, according to ACT 46/2000, the relevant signing off electrical engineer can be held legally liable for bad design if parameters are unchanged. So thank you so much for that.
Thank you.
Thank you for that input. Okay, sorry, let me go to the next question. why should UL be higher than UO?
Why should UL be higher than UO? Okay, I did explain that in the presentation. I'll explain again. UL is UO is your overall uniformity. It ensures the smoothness, if you like, of uniformity of light. If you like, if you could compare it to butter on a knife, spreading it over your bread, over a slice of bread. That's your overall uniformity, and this is for you've got performance and you've got visual comfort. So performance is your overall uniformity. But you're asking, why is longitudinal uniformity more important than overall uniformity? Longitudinal uniformity is for, remember, we're working on an A-class road, so the driver is expected to be sitting on at 1.5 meters above ground level, facing in front of them for quite a considerable amount of time. And this is where UL comes in, because this is visual comfort, where we get rid of that zebra effect, so that we can negate fatigue, visual fatigue, which obviously ties into visual performance. And it always comes down to it's safer. It is a safety issue.
Okay, thank you. Then the next one, does Ulysses consider lighting levels of emergency lanes? If not, then these designs are potentially compromising public safety.
No, it does take into consideration emergency lanes. We will always show the candela per square meter value with the UO, with the UL, with the TI. We can also show the illuminance levels. It doesn't not take it into consideration, but again, the standard doesn't require it. It's required for the driving lanes. But we'll always include it. It's not an issue for us to include it.
Okay, thank you, Retief. Then the next one, Ulysses is an international toolkit for streetlights design, I suppose. Is it programmed to acknowledge minimum lighting level of each country when designing? In South Africa, SANS 10098-1 will most probably specify these parameters, as I think a standard in Belgium, where Schréder is, specify according to that country. Do you calibrate, or how do you mitigate conflicting standards?
Okay, that's a good question. I enjoy that question. Yes, Ulysses does take into account the relevant international standards, and it's part of the, for lack of a better term, bloatware of the software. You have your M classes and A classes and P classes, which come standard as loaded constraints. And then once we have it in South Africa, once we get Ulysses in South Africa, like we do, we take the standards and we create our own constraints as per SANS 10098 part 1. So we have our A, B, and C classes.
Okay, here's the next one. Do you have training seminars on Ulysses software?
Yes, we often do. Unfortunately, due to COVID, the physical training has obviously stopped for now, but it's not something. It's something that we like to do and give training on, and I'm sure this is something that can be arranged.
How do you incorporate the land surveyor road layout into design consideration in relation to road contours?
Okay, if I understand that question is, correct me if I'm wrong. How does the undulating levels of, if you like, the undulating ground affect the street lighting calculation? Well, first of all, when working in Ulysses or working in any type of road lighting calculation software, be it Ulysses or Dilux or Relux or AGI or Lighting Reality, you will always work in a theoretical, as per CIE 140, you will work on a straight road. There's no undulation. There is unfortunately no way to calculate for a road that might have a bunch of bumps going up and down in a high at a high frequency. So we work for straight long roads. Then what we will do, once we've calculated the best spacing on a straight road with a specific luminaire, with a specific geometry, with a specific setback, with a specific outreach arm and overhang, we would then take that spacing and apply certain factors to it. For instance, once, let's say we have a plan of a road that the client provided to us, where there are many curves in the road, we would take SANS 10098 part 1 and apply a curve to spacing ratio, so that, let's say, we calculated on a long straight road for a specific class road, the spacing should be 40 meters, but now there's a curve in the road. Obviously, we can't maintain that 40 meters because we're going to start getting areas of darkness. We have to apply a factor which we have to calculate for that spacing. So for instance, where it was 40 meters on a long straight road and we've calculated the necessary factor, you could end up having, depending obviously on the angle of the curve and how sharp it turns and how quickly it happens, you will always see a reduction in spacing from the optimal spacing that was calculated in Ulysses, and that we do then in our other software packages, but we use AGI 32. I hope that answers that question.
Thanks, Retief. Then we have another question. What are the standards for luminance, illuminance, etc.?
Okay. What are sorry, the question? What was it? What
are the standards?
Well, for luminance and illuminance on road lighting, it's 10098 part 1 and 2 for different types of part 2. You're starting to deal with other types of things that happen in roadways, such as toll roads, toll gates, and then we start looking at adaptation and transition lighting. But yeah, it's for exterior lighting on roads, you're looking at the SANS 10098 part 1 and 2.
Thank you. Then should we use the lux to candela per square meter conversion for site measurements with a lux meter for type A roads?
No, it's a thumb suck. That is my quick answer is no. It might give you a good idea of what you're achieving there, but it's not accurate. I would much rather use a calibrated luminance meter and measured correctly also.
Thanks. So here's a question, sorry. So I think going back to the IES and LDT files, so does BEKA's photometric files that can be obtained from the website comply to the data file information requirements for IES and LDT files?
I don't think they're available on the internet anymore, and it's actually something that's been discussed at BEKA, and it's purely because everything changes so quickly. So we would rather, once the client asks, we would give the most up-to-date files. However, when you say does it comply to what was the question? Sorry, I remembered it says, does it comply to something?
So does BEKA's photometric files that can be obtained from the website comply to the data file information requirements for IES and LDT files?
Yes, I mean, we try to. If it's our own product, generally yes. There might be instances where one luminaire was scanned with one optic and the rest has to be created based on one inferred set of data. But in general, yes, especially on our road lighting luminaires, they are all compliant and what's the word, all trustworthy. They're accurate when we create them. There might be issues that are sorry, I say issues. There might be what's the word? When you look at all the inherent information to a specific luminaire, it might not say manufacturer. That might have been lost out of it, but it's not something that affects the performance of the luminaire or the photometry in question. However, it is something that we are looking at quite thoroughly in the meantime, and we're working on a standard way to populate, especially for the ULUM-DAT files, because they obviously have a much bigger array or data set.
Thanks. Then is the Ulysses lighting design software available for use, or is it an internal software package? We normally use Relux.
Yeah, no, it's available. I'm sure it's available to clients. They just need to get in touch with our marketing department.
In your calculation, you used a MF of 0.8. Why is that? Why not use a value lower, since the luminaires are used outside?
Okay, no, look, maintenance factor is a 0.8 maintenance factor for street lighting is actually quite conservative. If you mean lower by, we need to take into account a higher dirt depreciation or something, this is actually quite a conservative maintenance factor for this type of installation. If we were to use, for instance, 0.7 maintenance factor, taking into account, I mean, if you go and look at the dirt depreciation I mean, we're looking at the 0.83 for an IP6X rated luminaire. So it could be IP66, IP68 in a very dirty environment. You're looking at 0.83. So I mean, this is actually very conservative. We would, and I mean, just because it's outside doesn't necessarily mean the dirt depreciation has increased, because of, it could be the mounting height, the luminaire is facing down, there might be no rake. There's so many things to consider. My short answer is 0.8 is conservative. It's very low. In fact, I would rather ask, why are some people using 0.9, 0.95 and almost unity?
Thank you. In the old days, they used to refer to primary and secondary roads. How do they equate to the class A, B, and C type roads?
Okay, I mean, it's actually quite clear on the table. If you go look at A class roads or B and C type streets, you will see that actually let me go to that table. Here you will see an A1 is the type of road is described as a freeway and expressway with, and there should actually say or without a median, free of level crossings for speed limits exceeding 90 kilometers per hour. A2 is a major road for speed limits not exceeding 90 kilometers an hour. A3 is important urban traffic routes for speed limits not exceeding 60 kilometers an hour. And then A4 is your typical connecting roads, local distributor roads, residential major roads. And then obviously your B, it explains it there. But then the question is primary and secondary roads. I think generally your A-class roads, I think you would have primary and secondary in both classes. Your A1 to A2, maybe even your A3 could be primary A-class roads, within the secondary being your lower level of A3 to all the way to A4. And then the same for B. You could have a primary B-type road being your B1, and then the B2 and B3 could potentially be your secondary roads. But I'm speculating.
Okay. Do you have, sorry, I'm going to read this. Do you have LED bulbs that can replace street lights, 150 watt HPS, 250 watt HPS, and 400 watt HPS, so as to have a simple removal of of the bulb instead of replacing the whole fitting?
What is assumed in that question is that it is a matter of wattage, and unfortunately, this is something that is a misconception in technology, because HPS has a very high efficacy, and LED compared to HPS at this point is still at the lower efficacy, although we're creeping up to it quite quickly. So to answer that question, we have solutions in LED that can replace those luminaires if the application is done correctly. But to go measure flux to LED flux to HPS flux, it's not the correct way of doing it. The correct way is to, you see, what might happen is that in the old days, they might have used, let's say, 150 watt HPS luminaire for a B2 class road or a B1 class road, but they've grossly over achieved on the measured lighting levels, where you could potentially now replace that with an LED of a much lower flux value and a wattage value, but they can't compare with regards to wattage and flux performance, but you will achieve the required standard. We have post stops where we can interchange, like the BEKA Ray, the BEKA Star. We can change the internal lamps from the old Mercury Vapor or CFL with LED. We can do that.
Okay, then moving on, a rural gravel road. What type of road classification can it be seen as? B2 or B3?
Sorry, say that again. If what?
A rural, sorry, my English, gravel road. What type of road classification can it be seen as? B2 or B3?
No, I think the understanding of that is that the interpretation of that is actually not accurate. A rural type gravel road, it depends again on the speed. Obviously, you'll see that you have B1, B2, B3, which generally you have speed limits of up to 60 kilometers per hour. All right, and the street would have sidewalks, but for a rural type road, it's quite hard. You have to take into account the volume of traffic. Are there pedestrians walking there often or not? A study needs to be done to be able to say whether it's B2 or B3. What does medium volume traffic mean? What does low volume traffic mean? What are all the different risk factors in this area? If it's a road that's not traveled often on or walked on a lot, there's not a lot of traffic, then we can start reasonably assuming the lower end of the B class roads. But if it's in an environment where there's a lot of people living there and they're walking and it's just not been paved, it's gravel, then you could potentially look at it as at the higher end of a B1, but a study definitely needs to be done to get to the accurate answer.
Okay, thanks. Then, sorry, coming back to the question earlier, we actually misunderstood the question. So
which question?
I'll get there. I meant that what are the standard values for luminance and illuminance for street lighting? Like how you mentioned,
Okay.
Retief, that a full moon is 0.3 lux minimum.
No, that's at perigee over the tropics. But the standard values for luminance is candela per square meter, and for illuminance it's lux or foot candles.
Okay, I hope that answers the question. And then it looks like we are, sorry, I'm just trying to navigate here. Okay, so then we've got a a comment, I would consider 0.8 LLF/MF, sorry, the terminology, to be rather high for LEDs. 0.7 would be conservative. This is based on my studies of dirt accumulation on LED luminaires, which no longer have the burning off ability that HIDs had.
Okay, I mean, I wouldn't go as far as to disagree with that, not at all. But that is a subjective assertion, and I'm happy. I mean, if a client tells us, listen, please make sure you use a maintenance factor of 0.7 for your LED luminaire, we will always comply with the request. However, I will still say that I think the 0.8 is still very conservative. 0.7, yeah, you're now looking at an installation that will, I think you might actually at that point put yourself out of competition in certain senses. But again, if a client tells us use 0.7 as a maintenance factor, we will use a 0.7 as a maintenance factor. And I understand the burning off ability that HIDs had, but it's no longer the case. And again, I mean, it depends on the environment. If we're looking at the coastal area with high high moisture content in the area, and there's high humidity and lots of particulates, you know, then we need to see this backing up of dirt or accumulation of dirt onto the glass or onto the protector. So yeah, I mean, if that's what the guy would consider, definitely it's a good consideration. It's erring on the safe side, and that's great. But so is 0.8 maintenance factor, absolutely.
Okay, and then it seems we have a last comment. It is important to state that when replacing existing HID installations, it is not possible to do simple LED replacements due to varying photometrics or optics. We cannot simply do a wattage replacement, and existing installation criteria needs to be taken into account when doing LED replacement projects.
100%. I fully agree with that.
Okay, great. It seems that we don't have any questions anymore. So then from our side, we just want to say thank you so much for joining us. Please email us should you require recording of this webinar. This will also be available on our YouTube channel though by the end, well, we'll try for tomorrow, otherwise latest